So let's take a guess.
Okay.
Right? We wanted a short circuit.
Yeah.
Right? But now we know that the wire is made up of some material.
Correct.
Some copper. It's a copper wire.
Copper. Yes.
Right? So most likely copper is going to have some resistance. You take a much longer wire.
Correct.
You're going to have some resistance.
You're going to have more resistance,
Right?
which is fine.
So which means the wire needs to have some. It's not a short circuit for sure.
Okay.
You take a 10 meter long wire.
Yeah.
It's not a short circuit. So now let us maybe start looking at what
the wire is.
What the wire is, right?
Yeah.
So we have a long wire.
Yeah.
Right. And it looks like this will definitely have some resistance.
Resistance.
Right.
Yeah.
So I'll show this. So this is we'll show it like this. So I'll call this 1 and 1 prime, 2 and 2 prime.
Yeah.
We'll show it like this, right? So we are definitely going to have some long resistance. So 1 and 1 prime.
Yeah.
And see, my guess is that these two wires are separate.
Yeah.
Right.
But one other question is, yeah, so you justified resistance.
Correct.
Now, even if it was a very complicated resistive network,
Yes.
you cannot have frequency dependent
That's correct.
effects, right?
That's correct. So one guess immediately is I have two wires.
Yeah.
And now they have some rubber or something in between, which may have some dielectric constant.
Yeah.
Right. So my guess is that there's going to be some capacitance between them as well.
Okay.
Some unwanted capacitance.
Yes.
Right. So maybe I will add some unwanted capacitance as well.
Okay.
Right. This tells me that there is a frequency dependence.
Yes. At least it should behave like a low pass filter.
It should behave like a low pass filter.
Yeah. Fine.
Right. But something else is going on.
Yes.
Right.
Right.
What I am getting is something completely different from any low pass filter.
Yeah.
Right. Okay. So now, long ago, when we looked at a third component,
Yes.
which you get, we showed them, we made measurements on the inductor.
Right.
The inductor was actually made by actually coiling a wire.
Coiling a wire.
Right?
Yeah. And this one is like a mega coil, right?
It's a mega coil.
It's a messed up coil here.
That's right.
So you're saying that there is an inductance now.
there isn't most likely an inductance.
Inductance. Okay.
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 So my guess is even this is not good enough.
Okay.
Okay. So we actually need our model for this. Maybe this is a better model. Because
Okay.
the wire, because there is a long distance here.
Yeah.
And it's also coiled up quite a bit. There is going to be our theory is that there is some inductance as well.
Yes.
So maybe we will modify our expectation from the wire,
Yeah.
our model of the wire to include this. So 1 prime, 2 and 2 prime.
prime.
We'll make it like this.
Okay. So the 10-meter wire has been modeled as an equivalent resistance, inductor and capacitance.
And capacitance.
Okay.
Okay. And this one we have seen.
Yeah.
This one actually when we saw this earlier, this was also a low pass filter,
Yeah.
but it actually gave you better frequency response.
Correct.
Right?
Exactly.
So what happened is it actually gave you something that could give you, we said it will give you a better filter.
Yes, a higher order filter, which
higher
gave
order
you a
filter.
better drop.
Correct.
Right?
So
Right.
in fact, we did it in the, we wrote down the differential equation.
Right.
We said that it's a second order differential equation.
Yes.
Right? This gives you a second order differential equation. Because of that, it actually gives you a second order filter.
Right. Right.
Okay. Still doesn't explain
Why I got the sinusoid.
why you saw this particular ringing.
Exactly.
Okay. So maybe we'll go back to the second order differential equation
And start from there.
and start from there.
Right.
So I don't want to solve, this in detail, because when we did the filter, we
Yeah.
actually wrote down the voltages, currents, and showed that it was a second order differential equation.
Yeah.
We will go with a more generalized approach.
Okay. So
Right.
just before that, can I just interrupt you? Sorry there. So can you just draw that sinusoidal
Yes.
damping waveform
Yes.
here?
So we saw something like this.
Okay. So what does this mean? So you're saying that, okay, there's 1 volt. The capacitor is now, voltage has gone up.
Yes.
That means there's more charge on it.
Yes. So there is indeed more charge on
So
it.
if I look at the energy in the capacitor, half CV square,
Yes.
it is actually going up.
It's going up.
It's going up, and
Yes.
then the energy is going down,
Yes.
right? Because it's falling. Actually, if you
It is
look at
falling
that
down.
voltage,
Absolutely.
it's going well below.
Yes. It is.
It's coming all the
In
way
fact, it is
down
going
to
below zero.
Zero.
It is going below zero in
Right?
this case.
Okay, it's going below zero. That means it's sort of again losing energy.
That's right.
Okay, then it's gaining energy, but not all the way as it had in the first stage, and
That's
then it's
correct.
losing, and then it is settling.
That's correct.
So somewhere there is an oscillation of this energy
Correct.
kind
That's
of
right.
thing.
Exactly. Absolutely. So in fact, my guess is
Yeah.
that we know that an inductor can actually store energy.
Exactly.
But in the form of current.
In the form of a current.
Correct. So my guess is there is some interchange of energy between the inductor and the capacitor.
Exactly.
Right?
Right?
Absolutely.
Okay. So that's what is happening, right?
Yes.
Great. Okay. So as you said, now let's maybe write down the differential
Yes.
equation and see what happens.
Okay. So we will write down the differential. So this is this voltage was VO.
Yeah.
So we will write down the general form of this.
Yeah.
Right. So the general form, I'll write it like this. So let us say A times d square V naught by dt squared, because we said second order differential
Yeah.
equation, plus some B times dV naught by dt.
Yeah.
Plus we will have the linear term itself, and we will say this is the general form.
Right.
Okay. We will ignore the constant term for now.
Yes.
Right. So there may be a constant as well, but we will say this is the general form.
Yes.
Because for the purposes of our discussion, this is good enough.
Yeah.
Right. So when we looked at the RC filter,
Yeah.
so this is for this, right? The first order,
Okay, that can be obtained by just making A equal to
A
0.
equal to 0.
0.
Right. So A equal to 0
Yeah.
gave us B dV naught by dt plus CV naught is what we
Yeah.
can
C
have.
V naught.
We'll make it CV naught.
Yeah.
This is our general form of the first order.
Yes.
Now, when we solve the first order, I think we got an exponential
Solution. Correct.
And I think the way we can justify that is to realize that you are taking a single derivative,
Okay.
okay? You are scaling that.
Yes.
So, you are taking the scaled. So, this whole this is the scaled derivative. So, you are taking the derivative of V naught and multiplying it by some B.
Yeah.
And we are actually saying that is actually proportional to the scaled signal itself.
Input.
Input,
Scale solution
scaled
itself. Right. Scale solution. Yeah. Right.
That's right. So what this is telling us, scale solution rather.
Yeah,
Right.
solution,
That's
not
a
the
better correct.
Yeah.
So because V naught is the output as well.
Yeah,
right?
exactly.
So it is a scaled solution. So the scaled derivative seems to be proportional to the scaled version of the solution.
Yeah.
And this already indicates to us that you take some function f of x
Yeah.
and you take the derivative of that.
Yes.
This should be proportional to f of x itself.
Exactly.
This is what actually gave us the exponential,
Solution.
some e power
AX.
AT.
AX.
In our case, yeah, exactly, correct. So we'll just write it in the general form. So e power AX
is what we got. Yeah.
is what we got.
Yeah. So if you differentiate this, you get A times e power AX.
Exactly.
And some
So-
scaling will cancel out. Yeah.
This is the form.
Yes.
So in fact, maybe A e power bx, some form like this.
Correct.
Would be the general solution.
Absolutely.
Right. That is what told us that an exponential response will actually be a solution to the
Differential equation.
differential equation, the first order,
Perfect.
which was our RC.
Yeah.
Okay. So now we are looking at a generalized second order differential equation.
Yes.
Right. So let us see what we need from that.
Yeah.
So I'll write it again here. So A d square V naught by dt squared plus B dV naught by dt plus C times V naught is
Yeah.
0. This is our general form.
Yes.
So now this is telling us not only is the first derivative
Yeah.
related to V naught,
Yes.
the second derivative also seems to be, so what you are doing is you are taking a function, you are taking the derivative and scaling it, you are taking a second derivative and scaling it as well,
Again.
and they are all adding such that it's a solution,
So they are all of the same form.
all of the same form.
Yeah, but
Right.
I think exponential satisfies this.
Absolutely.
Also,
So
right?
there is some alpha 1 times f prime of x, and that is again a scaled version of alpha 2 times f double prime of x.
Yeah.
But you're right. Actually, an exponential should also be a solution for this.
Exactly. So you take the
Right?
a e power.
Absolutely. So your f of x, we said a e power b x.
Yeah.
Should be a solution.
Yeah.
Right?
It could for certain values of
it
a
could,
b.
Certain values of
Right.
ab.
Yeah.
So a, b and c.
Yeah.
So f of v naught of t
Would be an exponential.
could be an exponential. Some a e power bt.
Maybe call it alpha times beta t because there's capital A, capital B. We don't
Capital
want-
B, capital
yeah,
B.
yeah.
We don't want people listening it.
Yeah.
So we will do that. So alpha
Beta t.
e power beta t.
Yeah.
Right? Perfect. Right? This is a solution. Indeed.
Yeah.
Okay.
Absolutely.
Clearly, because you take the first derivative of this, that will also be, so this is of the form e power beta t.
Yeah.
This is also of the form e power beta t, and so is this one.
Yes.
And you can choose constants and signs of the constants such that a, b and c, such that this will give you 0.
This will give you 0.
Perfect.
Right.
So this is indeed a solution.
Right.
Okay. Now, but that's not what we are getting, right? We are not getting nothing like an exponential.
Yeah.
So this,
In fact, it's not an exponential.
It's an-
Should have been
exactly.
like rising asymptotically.
Exactly. So we wanted, so if this was the input, so we would have wanted something like this, right? Something like this. This would have given an
Correct.
exponential solution.
The V out of
So
t.
this is V out.
Yeah.
We're getting nothing like that,
Exactly.
right? So there needs to be some other solution.
Okay.
Okay. So we need to look for a different solution that might give this. So again, we need to look for a different solution.
Yeah.
Now let us go back to this equation again.
Hmm.
So what we want is we need to look for a function f of
Yes.
x such that the first derivative
Yes.
is a scaled version. Second derivative is also a scaled version.
Yeah.
Right? Do
So-
we know of any?
I think if you go back to what was taught in 11th and 12th standard, right?
Yes.
I remember this problem of a spring, right? You take a
Yes.
spring with a mass attached on a frictionless surface.
Correct.
You pull it
Correct.
and you leave it.
Perfect. So this is, I think, the problem that you're talking about. You have a mass m.
Yeah.
And this is a spring
On a floor. Yeah.
on a floor, on a frictionless
floor.
So I'll show it like that.
Yeah.
So, and correct. So you basically pull it, stretch out the spring,
Yeah.
and then release it.
And then release it.
So
Right.
it will keep going back and forth, right?
Yeah. Where
If there are
the
no energy
restoring
losses.
force is basically K times X.
K times x.
X, right?
That's right.
So can we just write that equation? It's not that, right?
Correct.
The F, and F happens to be what? F is actually minus Kx.
In this case minus kx.
Minus
because
Kx,
it's a, correct,
restoring force, yeah.
correct. It's a restoring force. So we'll
So-
write it like that.
M dV by dt,
Correct. So that is your
dV by dt
right
is equal to minus Kx.
minus kx.
And V is dx by dt.
V is dx by dt. Correct. Oh, I'll use the small v, which is the right way to do it.
Yeah.
So V is dx by dt, which is the velocity. Perfect.
So yeah, so this, if you write it down, it seems like a second order differential
That's right.
equation.
That's right. Indeed, it is. If you put these two together, so m d square x by
dt squared
dt squared is basically minus kx.
x.
Yes. And
Right.
this is indeed a second order differential equation.
Yeah.
And special case where the linear term, the first derivative term does not exist.
Exist, exactly.
And the solution for this was actually a
Sinusoid.
sinusoid.
Was a sinusoid, because we
Right.
know that, yeah, because
Yes.
it's basically this mass will keep oscillating back and forth now,
Yes.
right, about that mean position.
Yes, that's right. So what you are suggesting is a sinusoidal solution could be, a sinusoid could be one solution to this.
Yeah, because here if you take this d squared x by, I know that sine omega naught t, if I differentiate once I get cos,
Yes.
I differentiate again I get minus sine.
I get minus sine,
And-
and cosine can also be seen as a scaled, as a delayed sinusoid.
sine, exactly.
Perfect. Okay. And okay. So I think you're right. So the other solution that we are looking for might be a sinusoid.
Yeah.
right? Some omega naught t is what I'll call it. We don't
Yeah.
know, right?
We don't know, right?
We
Yeah.
don't know what that is.
Correct.
We'll call this sine omega naught t. So now, so what you are saying is, so if f v naught of t, if v naught of t, let us follow the same. So you said alpha e power beta t.
Yeah.
Here we'll write it as alpha alpha sine beta t. Shall we just write it like that?
Yeah, yeah.
Plus gamma.
Yeah.
Right? Gamma is the some phase.
Some phase.
Some phase. We don't know what.
Exactly.
Basically, this is the generalized form of a sinusoid.
Yes.
Right? And dv naught by dt is basically alpha beta sine of, oh sorry, cos of beta t plus gamma.
Yeah.
Right? And that's of course can be written as a delayed sinusoid again.
Yeah.
So basically this can be written as alpha beta sine of
beta t plus gamma prime.
That's
all. Yeah.
Right? And d square v naught by dt squared, again it should be clear because you again have a sinusoid.
Yes.
Right? So you can write this as alpha beta squared sine of beta t plus gamma double prime.
Right?
Right?
Or you just take the first expression alpha beta.
Correct.
And it will become alpha beta squared sine beta t plus gamma. Actually, you're back to gamma.
You're back to gamma actually.
With a minus sign.
With a minus sign.
Yeah,
that's all. Right?
Okay.
So it's so this is basically minus alpha beta squared
sine of
beta t plus gamma. Original gamma.
Exactly.
Perfect.
Right? Yeah.
Right? So basically, yeah, the first one gamma prime and gamma will differ by 90 degrees.
Yes.
The next one will differ by 180 degrees.
Yeah.
Because correct. So every differentiation adds a 90-degree phase shift.
Right.
Right. So it looks like you can get a linear combination of v naught, dv naught by dt and d square v naught by dt squared that can actually give you a 0.
For certain values of capital ABC.
Certain values of capital ABC.
Okay.
Right? It seems like this.
Yes.
Perfect. So, which means this is also a possible solution.
Yeah.
And okay, so now this makes a lot of sense.
Yes.
Because now I see why we are actually seeing this kind of ringing.
Yeah.
This is some kind of sinusoidal ringing that we are seeing, which corresponds to some, we have found out some values of the input frequency.
Correct.
And the amplitude and so on, the characteristics of the system.
So this does not happen for every omega naught.
It need not happen for every omega naught, and the omega naught might be functions of amplitude and input frequency and so on. We don't know yet.
Yeah.
Right. So we don't know that it is. But my gut feeling is that I am seeing that the characteristics of this is changing, even though we have not changed the input period. So that seems to be something fundamental to the system rather than my input period.
Correct.
Right? That's what it seems like.
Yes.
But great. But this actually tells me that definitely a sinusoidal solution is possible. If I had looked at this, if I had realized that there might be RLC.
Yeah.
And there is a second order differential equation, I should have guessed that there could be a sinusoid.
You can. Yeah. Actually, in 11th standard, we also do as part of simple harmonic motion, right? If you take a charged capacitor and just connect it to an inductor.
Yes.
Right?
Indeed,
maybe we can just look at that.
We can look at that
because
situation.
That is without.
Absolutely. Yeah. So maybe the case you are talking about is, let us say, I have a capacitance C.
Yeah.
And let us say I have a switch in series with it.
Yeah.
And I have an inductor.
Yeah.
And I'll take the simple case. I'll say that the inductor current at t equal to 0 is 0.
Yes.
But I'll say that the capacitor, so Vc of t of 0 is some 1 volt, let us say.
1 volt of 0 minus.
Of 0 minus, right?
That means it's initially charged.
Correct.
And then you're turning on that switch and connecting it to an inductor.
That's right. So I'm charging the capacitance to 1 volt and at t equal to 0, I'm turning on the switch.
Right.
Okay. So indeed, yes. So now we can write the differential equation for this system.
You can write it.
Right.
Okay.
And it will indeed give you a.
So we'll just do that.
Let's do that. Let's do that. Okay, so the way I'm going to do this is to well, I need to write my current. So now after the switch is thrown,
Yeah.
let us see. So the system looks like this.
Yes.
Okay, and I can write down the equation. So this is inductor voltage.
Yeah.
This is inductor current.
Yes.
And that same current is coming out from the capacitor.
Yeah.
And this is VC. So, well, okay. So 1 minute. We will do it like this. IC. So IC is minus IL because I want to keep the
Current. Yeah. Yeah. The current has to
directions
go into the
consistent,
capacitor.
Into the capacitor.
Yeah.
So that my equations come out right.
Correct. So
IC is of course minus IL.
Yes.
In this case. Then I can write out the component equations.
IC is
dVc
by dt.
C dVc by dt.
Yeah.
And I know that IL, VL.
Yeah.
VL is basically L DIL by dt.
dt. Exactly.
Right. I can put these three equations together. So this is basically minus L DIC by dt.
Yeah.
Right. And now I plug in the value of IC here.
No, how did we get
because
this?
we wanted the voltage across the inductor is what
Yeah.
I am doing.
Yes.
So VL is L DIL by dt.
Yeah.
And I have just said that IC is minus
IL.
minus
minus IDIC.
So I have just done
yes,
this.
yes.
Right. So now then
That is
right. So then I can just say VL is minus L d by dt of C dVc by dt.
yes.
Right. Yes, correct.
Yeah, C dVc by dt.
C dVc by
Absolutely.
dt.
Yeah.
Correct.
But VL is equal to VC.
Yes, VL is also equal to VC.
VC.
So that's the last equation that we need. So we'll write it up here.
Yeah.
VL is VC. So this is basically minus LC d square VC by dt square, which is minus LC d square VL by dt square.
Yeah.
Perfect. So you have got this
Equal to VL.
spring mass system type of equation.
Exactly.
Right?
Right.
We got this m d squared x by dt squared is minus kx. We have the exact same type of equation
Exactly.
here. So we want to solve VL is minus LC d squared VL by dt squared.
Yeah.
Okay. So this is the equation.
So
sinusoidal solution.
You'll get a sinusoidal solution.
Absolutely.
So what this is telling us is there is the energy of half CV squared on the capacitor.
Correct.
It sort of is being transferred to the inductor.
To the inductor.
Right.
And then the inductor transfers it back to the capacitor and so on.
So this is like this oscillation. So when will it stop?
It will never stop.
So
if you
it's
have an
like
ideal
that
inductor and ideal capacitor, it should never stop. It's like that frictionless
mass, right? It just keeps going on and on and on and on forever.
That's right. That's right. So if you look at this voltage, so it will basically look like this, right? So if I plot it as a function of time, it will continue to
just oscillate.
Continue, right? With going from +1 to -1.
Yes.
Right? Forever.
Absolutely. Forever.
Forever.
Right?
Because I have nothing to lose, nowhere to lose that energy.
Exactly.
The inductor and capacitor don't lose energy.
Don't
they can
lose
only store
energy.
it.
Exactly. Right? So where might the damping be coming from then?
The one component I know
Yeah.
that removes energy is a resistor.
Is a resistor. So
Yes.
you're saying like in the mass system, if I have friction,
Yes.
at some point it has to stop.
It has to stop.
Right? And the amplitude will keep coming down with time.
Until it will stop.
Right?
Correct.
Okay.
So in this case, now I'm going to take a guess. So
Yeah.
if I were to take the same system
Yeah.
and put a resistor in parallel with this.
Okay.
Okay. So let us say R.
Yeah.
And now I charge the capacitance and initial voltage was 1 volt. My guess now is that over time,
Yeah.
I will actually start seeing it slowly die out.
Die out. Right?
Yes.
Because there's some current that will flow through the resistor
Through
each
the
time.
resistor every time, and we know I squared R is the
It'll
power
get-
dissipated. Over time, you get energy
Yes.
lost in the resistor.
Okay. So initially it's half C into 1 volt square.
That's
Next
right.
time it would have lost some energy through the resistor. So it will go slightly lesser,
Slightly
0.9.
lesser. That's
0.8, 0.7, and eventually it has to just
Correct.
stop.
It has to stop. Eventually, you will reach a point where all of this original half CV squared
Is lost.
is lost in the resistor.
Okay.
Wait for a long enough time.
Okay,
So it will
interesting.
start off with +1, but maybe by the time it has hit this, it's already not -1.
Yes.
We don't know.
Yeah.
Right? But this tells us that you can actually create, and in fact, now this tells me I'm able to correlate because it looks like this value of resistance R seems to have something to do with that.
Exactly.
Right? So the fact that it is actually in my, I'm seeing that slowly that ringing is dying out tells me that most likely it may be due to this R.
Right. Right. And so that seems to be, okay, very interesting. So, but this does not seem to happen for every frequency, right?
It does not seem to happen for every frequency. Yes, because you need some specific values of A, B and C.
For
right?
the sinusoid.
For the sinusoidal solution to be valid.
Valid.
That's right.
Right.
Okay.
Okay. So that's why the
if you choose a
RLC value.
RLC values matter. So if you choose a different length of wire, it will be, the response will be very different.
For that ringing may happen at a different frequency now.
Most likely will happen at a different frequency.
Wow. Okay. So this is interesting. So as far as our experiment of sending data, right?
Yes.
You're saying fundamentally we are limited by how fast we can send the data. You cannot
That's
send
right.
it at like gigahertz
That's
over
right.
a wired line like this.
That's correct.
Right.
So if you take this cable, so now what our just concluded discussion tells us, if you use a better wire, a different wire,
Yeah.
you can actually with maybe lower R or different value of L and C,
You
you can actually send at 1 megahertz or beyond as well.
Okay. So it seems like our cable TVs, right?
Yes.
They use these coaxial cables which can actually receive like much higher
Hundreds
data
of
rates.
megahertz.
Hundreds of megahertz, right?
That's right.
And okay, so that's a great way of transmitting. But for the telephone, I think this is okay because the bandwidth, the frequency content there again is voice. We go back to
voice.
our discussion on the voice.
That's
right.
right.
Sampling rate of 8 kilohertz and all is okay.
Correct.
So maybe this is okay
This
for
is
that
fine, right?
purpose.
This is fine to just send the information across the room.